Welcome and hello. Today we are going to try to demystify and explain recent approaches to improve the cybersecurity of enterprise, critical infrastructure, and specialized mission systems. Basically anything that has multiple computers, users, and software applications that interact and exchange information and data via a network. Specifically, we are going to dive into something called Zero Trust and discuss various architectural approaches to implement Zero Trust in our systems. Right now you might be asking yourself, what is Zero Trust? How can it improve cybersecurity? There is much confusing and conflicting information out there on Zero Trust. What are the essential concepts? I work for the U.S. federal government and my organization has been told to develop a plan to implement Zero Trust. Where do we start as an organization? If you're asking yourself these questions, or even if you are just curious to hear our take on Zero Trust, then this is a great video for you and we hope you get something useful out of it. Before we get going, we should introduce ourselves. My name is Jeff Gottschalk, and my colleague is Christopher Razor. We work at MIT Lincoln Laboratory. Our mission is technology for national security. We are the biggest of the U.S. Department of Defense's 3 laboratory-focused, federally funded research and development centers, or FFRDCs. Basically, we are a nonprofit research and development organization in the Boston area run by the Massachusetts Institute of Technology, aka MIT, on behalf of the DoD. While we mostly work with the DoD, we also work with many other parts of the U.S. government. Chris, for example, is the Assistant Division Head of our 300-person Homeland Protection and Air Traffic Control Division, working closely with DHS and the FAA, among others. I am the Assistant Division Head of our 300-person Cybersecurity and Information Sciences Division, working closely with the FBI, the intelligence community, and of course, the DoD. With that out of the way, let's begin our journey towards Zero Trust. Enjoy. So our director, Dr. Eric Evans, asked us to perform a 6-month study during 2021 about Zero Trust architectures. So we formed a team to look at that. The study has multiple outputs. Today you're going to see one of those outputs that we'll go through today, focused on giving you an idea of what Zero Trust is and what some of the trade-offs are with understanding that. Cybersecurity incidents continue to be an issue, and they continue to be concerning, whether they're data breach issues like OPM, supply chain issues like the SolarWinds attack, or ransomware attacks like the Colonial Pipeline attacks. And it's one of the reasons why in 2021 that the federal government issued some guidance and plans for improving the U.S.'s cybersecurity strategy. The elements of that strategy are shown in the tan box on the right side of this chart, and the italicized and blue items are ones that are particularly relevant and germane to Zero Trust. And we'll talk more about that today. Our study team, because it was interdisciplinary and comprised of both cybersecurity operations experts, cybersecurity researchers and technologists, and people who build IT information decision support systems for the government, wanted to come up with a definition of Zero Trust that would work with our study team. So this is it. Zero Trust is a set of security principles that treats every component, service, and user of a system as continuously exposed to and potentially compromised by a malicious adversary. You can see our study objectives in the lower left-hand side. What I want to spend a little time talking about is, as we talked to a variety of parties about Zero Trust, we found out that there are a lot of misperceptions about it out there. So it's not about having a very specific cybersecurity standard or a clear end state design. It's not about outsourcing your work to someone so they can build you a Zero Trust thingy. It's not about dumping all the IT that you and security infrastructure you currently have and starting new. And it's not about locking down systems so strongly that they're not useful for their intended function. As I had said earlier, we have a variety of outputs from the study, and the one you're getting today is sort of what we refer to as the 101 version of this, focused on education and outreach. Some general takeaways from this are that prior security models were fundamentally flawed because they assumed that cyber threats could be kept out of systems and did not holistically apply important security principles that have been understood for 40 years or more. There's not one size fits all approach for Zero Trust, and that's why piloting, testing, iteration is very important. Not all systems, particularly critical infrastructure and mission systems, will be capable of doing everything the full zero trust way, and we'll have to have adaptation. Again, why iteration and experimentation will be important. We also talked to organizations that have actually done implementations of zero trust, and all of them have indicated that significant organizational commitment and change was required to be able to implement those. And lastly, we feel that R&D investments that the government makes needs to look not just at zero trust technologies itself, but also beyond that as threats will evolve. So we'll give you a lay of the land of zero trust, and I'm going to hand things over to my colleague, Chris Razor, who will cover the first sub-bullets here, and then I'll come back to talk about implementations and then lead into an overview of the use cases that we looked at in the study, and then talk a little bit about technology future directions and summarize. Over to you, Chris.
All right, thanks, Jeff. So for this next section, we're going to talk about the origins behind zero trust as a security principle, and then I'll also cover some of the guidance that's been issued to date and some of the testbed activity. So there have been cybersecurity incidents nearly as early as there have been existing computer systems. And this is one example of an incident associated with MIT, where both Jeff and I work. MIT was developing an operating system called CTSS. And not only was it a research project, but they were also using this operating system to monitor and facilitate use of their IBM mainframe for multiple users. And as it turned out, there was one user who wanted more computing time than they were allocated by policy by the folks that were running this mainframe. That the policy for this particular user allotted them 4 hours of compute time per semester, which was not a lot in those times, and certainly not a lot today. So the first approach that this user took was to abuse the privileges that he'd been given and modify the operating system so that the counter that was monitoring his own usage time automatically zeroes out when it approached its limit. So this allowed him to continue using these resources, beyond what should have been allocated by policy. And he did that until his coding privileges associated with monitoring this operating system, were lost as part of his research project had ended. The second approach that this user took, since they still wanted access to this machine, was to print out the file that contained all of the passwords for users of the system. It turns out that he couldn't look at the file itself, but he was able to send that file to the printer and then read out the print off. So he shared that with some of his fellow grad students. And again, that was a way for him to circumvent the security policies that had been put in place to continue using the system. And that ended when one of the staff monitoring the IBM mainframe noticed that someone appeared to be logged in who he knew was out of the building. So both of these attempts are examples of a user circumventing the restrictions that have been put in place by abusing really privileges and access that they had been granted. And these are exactly the types of actions that the current push in zero trust security are meant to prevent. So not long after these computing systems were starting to be in wide use, in the mid-70s, Salter and Schroeder produced a seminal paper that really laid out the foundational security principles that one would want to pursue in designing systems to be more secure. This paper described the 3 types of security violations. They used different language at the time, but today we know these as confidentiality, integrity, and availability. And this paper also laid out 8 security principles that designers should follow in order to make their systems more secure. This nomenclature has stood the test of time. It's still what's used in the community today. And so on the next chart, we'll define a little bit what each of these terms mean. So by and large, these 8 security principles can be divided into 2 categories. The first one, or the first set, are focused on design and implementation. And the objective here is to reduce the likelihood that any piece of code within your system has a zero-day vulnerability present. So approaches like open design or economy of mechanism, where you keep the code itself as simple as possible, those are meant to enable your code to be reviewed and audited, so it's less likely that a zero-day vulnerability is present. The other 5 security principles that were laid out in this paper have more to do with the operation of a large-scale computing system. So things like separation of privilege and least privilege are meant to afford access to users only as much as they need and limit really the reach of any one person widely within the system. The principle of complete mediation is meant to require attackers to repeatedly pass checks, both for access and for identity, that makes it harder for malicious presence to be maintained inside of a system. Fail-safe defaults are fairly self-explanatory, and psychological acceptability is about designing a system so that the security principles or the implementation of the security principles themselves aren't so onerous to the user that the user tries to avoid them or circumvent them and really defeat the purpose. What our study team did was to look at a number of security incidents over the past 25 years or so and categorize them according to which type of violation these incidents referred to: confidentiality, integrity, or availability. And then also which of the security principles that we just talked about were most relevant to the scale and the impact of the incidents that we're listing here. And what we find here is that while certainly these incidents have evolved over time, starting in the mid-2000s, there certainly has been a focus on confidentiality violations, mostly having to do with gaining access to large databases of information and exfiltrating them, whether it contains information of military use or individuals' credit card or financial informations, et cetera. Of course, recently we've seen a spate of availability attacks like the Maersk shipping line and Colonial Pipeline, where key pieces of infrastructure have been taken offline. But what we also noticed in the course of this study was that while a number of these incidents have zero-day vulnerabilities associated with them, and those are associated towards the top of this plot, what we see is that the vast majority actually are due to the exploitation of these operational security principles. That is, the gaining of individuals' credentials and the movement within a well-connected network that allows users to really gather a significant amount of information or have very widespread effects. And so really what we found is that this is the real focus or the motivation behind zero trust as a security approach, is the recognition that a number of these violations are due to these operational security principles that need to be enforced in new and better ways. So as we talked about already, our definition of zero trust is that it really is just a set of security principles, and it treats every component, service, and user of a system as continually exposed to and potentially compromised by a malicious adversary. A zero trust architecture is a computing system that is built following the zero trust principle. Of course, it's built to support its intended mission, and it protects its data and applications following what's most required in terms of confidentiality, integrity, and availability. And the implementation of these architectures, commonly includes a number of components, and those are listed towards the bottom of this chart. Things like identity verification, access control, and resource protection really cover the ability to verify a user or a device should be on the network, where they can go, and what data and applications they should be able to access. Those three are generally coordinated by a policy and orchestration layer. And that set of actions are then connected to the personnel that are overseeing and managing the system through a layer of monitoring analytics, as well as a set of continuous operations, a process really, to manage risks while supporting usability. Graphically, we lay out those elements within this framework. We draw the identity verification, access control, and resource protection as an event chain, because in our mind, it really does follow a set of steps to go from a user accessing a system to eventually getting to the resource that they desire. And again, as we sort of mentioned, those three plus policy and orchestration is really where zero trust is implemented within a system. And the items in blue are typically the cybersecurity professionals who are monitoring the system and providing updates as needed. Lastly, in this section, we just want to touch on how these zero trust components or functions, how they enable these cybersecurity principles to be implemented. So as we mentioned, identity verification, access control, and resource protection really go together. And the three of them allow you to then implement this concept of complete mediation, checks for every access request to every piece of data at whatever scale and time, whatever time cadence is most appropriate for the system. We talked about policy and orchestration, monitoring analytics, and continuous cybersecurity operations to support those implementations. And lastly, I think we want to make the point that the point of what's not addressed here. And so that is these principles of open design, economy of mechanism, and least common mechanism. Zero Trust is really not trying to implement them because their focus is to root out zero-day vulnerabilities. And that's not the focus of Zero Trust. A Zero Trust architecture might be designed in a way so that you mitigate the impact of a zero-day vulnerability if it's exploited by an attacker, but it's not trying to reduce the likelihood that any system has a zero-day vulnerability within it. So let's go on to talk about some of the guidance that's been provided to date, especially on the US government side, and some of the testbed activity that's underway. So as part of our study, we looked at a wide range of reference material. Only a few of them are shown here graphically, but we looked at everything from the introduction of Zero Trust as a term, which was introduced by Forrester Research about a decade ago, all the way through to kind of current cybersecurity strategy documents that are published by various agencies within the DoD and elsewhere. One theme that we found in looking through this and reviewing this documentation is that there is a difference between the framework that we're proposing and that which appears to be emerging as the consensus within the US government in describing Zero Trust architectures. And the difference stems primarily from the definition of what a Zero Trust architecture is. In our view, we're laying out a security principle that points to a set of jobs that need to be accomplished within a computing system in order to make it more secure. The emerging government consensus starts with a definition really, which talks about components and specific functions that need to be carried out. And so really, they're looking at things like identity and devices and data, rather as specific functional jobs like identity verification and access control. Both of these frameworks are useful and frankly needed in order for the government to effectively develop and operate Zero Trust systems. But the starting point that's been adopted to date sort of colors the set of guidance documents that have been the focus by the government up until this point. So what we're showing on the left in this table is a subset of the guidance documents that we reviewed. And the columns going across are our view of some of the elements that you want if you're looking for guidance from the government on what to build and how to build it when it comes to Zero Trust architectures. So all of these documents do a fine job of laying out the visions and goals behind developing Zero Trust architectures. They establish a common lexicon, and they're able to enumerate the various system components. What they don't do as well is provide canonical system designs. So for a program manager or an implementer who would be asked to develop a system, they don't really have a reference architecture to look to in order as a starting point. Another shortcoming that we notice is that there is not really talk of long-term maintenance and sort of long-term development from a roadmap perspective. So there are some short-term action plans, one produced by the Office of Management and Budget, for instance. But really there's a lack of guidance on how to think about long-term evolution of zero trust systems once they're put in place. And finally, we just noticed that essentially all of the guidance that's been provided to date applies to enterprise networks, not the sorts of tactical mission systems or critical infrastructure, which the DoD certainly and the US government more broadly does need to maintain, and naturally often interfaces with enterprise systems that are performing analytics associated with analytics on the data coming from those systems. So those are open areas that need to be addressed. Some of the work to fill some of those gaps is happening within the testbed activity that's going on right now. So while there isn't a place where you can go for guidance in terms of a system design, there are test beds, those developed by NIST and another one by the ATARC ZT lab, which allow prospective program managers to talk to those organizations, understand what testbed activity is taking place to date, and try to learn from the implementations that have been attempted there. So these are great activities. We think they should continue. I think from our point of view, they're not as well as centrally coordinated as perhaps they could be from the government perspective. But again, the US government's in a place where they're just getting started in organizing around zero trust. And we hope this is an area where they continue to focus on in the future. So just to summarize sort of our findings with respect to the guidance that's been provided to date. It's a great start, but there are still a few gaps. We see program managers as needing help in deciding what to acquire and how to architect their particular system. One of the ways that they could get some of this guidance would be for the government to support the development of 2 to 3 canonical implementations that are designed in a broad enough fashion that they address a number of similar use cases. Another place inside of our zero trust framework where we see a gap is in developing standardized metrics for monitoring and analytics. There have been some good initial efforts to date by NIST and CISA and others. That needs to be centralized and codified in a way that we can provide essentially requirements or guidance to program managers on how to design these sort of monitoring and analytics components. There are some test beds that are in development. That work should continue. We think that needs to be well coupled to challenging adversarial testing. Some test beds are focused on that and others less so. And so we think that would be an important addition. We did not really talk about this up to this point, but we do understand that both CMMC and RMF compliance guidance apply to government systems as well as defense industrial-based contracting systems. And that compliance perhaps needs to get updated in the face of these various emerging zero trust approaches that are trying to provide security at the same time as CMMC and RMF are trying to give guidance on how to appropriately implement it. And finally, we feel like a number of smaller government agencies who perhaps don't have the funding or the manpower to effectively implement some of these zero trust approaches on their own, they would benefit from a government engineering team that could provide expert consultancy or perhaps assistance in developing some of their development and deployment plans in order to make that a reality. And in our view, both NIST or CISA would be a great potential sponsor for such a team. And with that, I'll hand it back over to Jeff to talk about some of the recent implementations.
Thanks, Chris. So one of our objectives for the study was to talk to a bunch of organizations that have done implementations that work towards zero trust. and learn from them and be able to explain that to folks that are just beginning their journey towards zero trust so that they can understand what those options are. We also took a little bit at the marketplace of products and services that are available in this space and tried to characterize that as well. So we'll get into a little bit more detail here. But first, before we get into specifics, we want to take a look at those zero trust components and use that to characterize sort of where we are in a current state in most a typical corporate enterprise network, and what a future state that embraces zero trust, what its objectives would be. So just thinking about the current state today, a lot of organizations have different ways for people to authenticate and log on to systems. And many of those have been aggregated for expediency into single sign-on capabilities, just to make it easier for people to log on to systems. They have many of these systems today in terms of access control have all-to-all connectivity as sort of a default mode, and that's on all the time. In terms of access to resources and protecting them, they're encrypted when data is at rest, not when it's in use, or it's encrypted when it's being transmitted in a wire or over the internet. In terms of there's survivability to cyber attacks, there's redundant applications. The configurations of all these systems tend to be somewhat static. And there's a lot of monitoring at the edges of networks and at particular endpoint devices, computers and servers and so forth, but less in the middle. The cybersecurity operations is heavily based on compliance checking to make sure that security is good. But we envision a future state that embraces zero trust, where identity verification is enabled by cloud-based identity that's portable and ubiquitous and very secure itself. That access control is brokered, one-to-one connectivity as needed on demand. That resources are able to be protected in ways where encryption and authentication to do decryption are provided just in time. That data has provenance associated with it, so that as users touch and interact with that data, that's all capable of being monitored and logged and understood. And that applications are not just redundant, but made resilient in certain ways to cyber attacks so that they can keep working in the face of an attack. The policy and orchestration itself would be more dynamic and adaptable, and that monitoring and analytics are integrated system-wide. And rather than just relying on compliance testing, that compliance for cybersecurity, that periodic adversarial testing is done in specific ways to show that the architecture has been hardened and made resilient to cyber attack. So we'll start off with access control, and its integration with identity verification is one of the linchpin concepts here. We want to move from an environment today where each device can exchange directly with every other device to a zero trust network access, or ZTNA, environment where identity of users of those devices are verified, and then every access is mediated, logged, and analyzed. This concept enables different pieces of the network to be connected at different times as needed, and that concept is referred to by many in the zero trust community as micro-segmentation. We'll get into a practical example of this next with this user story. We have here a diagram of what might be a typical corporate local area network. It consists of users and servers, user computers and servers connected behind a network switch, that local area network, with connectivity out to the internet as indicated by the Google icon. And there's routers and various protection systems, firewalls, and so forth to prevent people from coming across the internet and into this network. We have a user here notionally connecting, coming into the office, connecting a laptop to the network. And in the background on that computer is a software agent called a network access control agent that takes its computer address and presents that to a database, which then communicates with the network switch and says, I've seen this network address for this computer before, please allow it onto the network. And at that point, user one can interact with any other computer on this network. And one way we can verify that is if user one uses a network protocol called ping. It communicates with other computers on the network, and they can ping user N's computer, and it will respond with a set of information that says that user N's computer exists on that network. Now, this is great from connectivity and making things very network centric, but it's somewhat scary from a cybersecurity perspective, as we'll explain next, in terms of the attacker's view of what they're able to do in this type of situation. Despite having a firewall in place, an adversary can get inside and establish a presence on a user's computer if that user accidentally clicks a malicious link. And from there, that user in this story, this attacker in this story can steal user one's credentials and masquerade them. And that's why their icon has changed from that little demon shape to a two-face icon indicated here. The complexity here is that they're using users one credentials and appears to most of the systems as user one. They just don't always act like user one. And from there, because everything's connected, they can pivot and laterally move within this network and establish presence on other computers inside this network, amplifying their attack. This is something that we'd like to stop, and we think Zero Trust can help with it, specifically access control. So now if we think about what access control is trying to do, we're really replacing that network switch with a fancier switch called a Zero Trust Network Access Controller, or ZTNA controller. Now, those lines that go out to the internet and the lines inside the local area network aren't just solid lines, they're dashed lines because they're off by default. The connectivity is off by default. And what's required are software agents called ZTNA connectors running on all the endpoints, the computers and servers and so forth, that are able to communicate with the ZTNA controller and establish connectivity when needed. So now when the user one comes into the office and connects their laptop to the network port, they fire up a software application, much like we do with VPN applications today, called the ZTNA connector app. And they're asked to do a multi-factor authentication of some sort. Maybe they're entering a username and PIN. Maybe it's some other multi-factor authentication thing that they do. And the ZTNA connector then communicates with the controller, and the controller verifies user one's identity and checks user one's policies. And it establishes that user one, using this particular laptop, is allowed to access certain parts of the network. In this particular case, user one is allowed to connect to server one, but nothing else. And we can show that they don't have connectivity at all, because when they try to ping user N's computer, the controller says, I don't know who you're talking about. User N is there and they're active doing other things with other resources and other users on the network, but not with user one. And so user one really can't reach out and interact with user N or server two. Now you might be saying, well, that seems very limiting for user one. What happens if user one has a legitimate business need to access information on server two? Well, a way to do that is shown here, which is that they would make a request to have connectivity to server two. And that can all be handled by policy in the background. The policy in this particular example says that in order for them to have access to server two, they just need to re-authenticate and verify their identity again. And so they're presented with an opportunity to do multi-factor authentication again, and they're granted access to server two. Perhaps not indefinitely though. Perhaps they're given a timeout window to have access to server two. In this example, we've picked 60 minutes. And at the end of that 60 minutes, then their connection to server two would be severed unless they re-authenticate to continue to have access to server two. This might be a minor inconvenience to user one, but it's a major inconvenience to the attacker, as we'll show here. Now, the attacker has moved from user one's computer to server one because they have connectivity to that, but they really can't get to any other part of the network. We've really stopped their lateral movement. And so when they try to move somewhere else, they can't discover anything else because the Zero Trust Network Access Controller says nothing else is on the network even though it is. And if the attacker starts to blindly lash out and guess at things that might be on a network, that can actually be monitored and logged. And when that happens, policies can look at that and say, someone, it seems to be hijacking user one's credentials and flailing about on this network. By policy, we will shut user one off of the network, and that will stop the attacker as well. They won't be able to exfiltrate any information out to the internet because they'll be disconnected from it. And that will allow security professionals to come in and actually do remediation of this cybersecurity incident. So we think that's a powerful concept. Another one that looks at the interaction of identity verification and resource protection is indicated here. We'd like to be able to transition from an environment where only bulk data is encrypted. So imagine your laptop, when it's off, that data is encrypted at rest. When you turn on that computer, your entire hard drive volume is unencrypted and you can work with it. If you send a file to a friend on another computer, that can be encrypted, so it's protected as it transits the network. But when they open up that file on their computer, it's unencrypted again. And the problem with that is that if their computer is owned by an attacker, that attacker then can take that unencrypted copy of that file and exfiltrate it. We'd like to be able to move to an environment where each data access, rather, is mediated, logged, and analyzed, as shown on the right. And in this particular case, just-in-time sharing is enabled by having keys that can be shared between the two parties that have to collaborate on this document. The file, even when bulk unencrypted, is encrypted by this other key that can only be exchanged by verified identities of those users. So now if the attacker is in the middle, all they're getting is a copy of a different encrypted file that they don't have the privileges to get the key for, and therefore they can't make use of it. That's the concept that we wanted to communicate here with just-in-time authentication. When we think about organizations that have applied these concepts of identity verification, access control, and resource protection, and the policies and orchestration needed to coordinate them, they break into three major categories. We talked about 9 or 10 different organizations, both commercial and government. When we did this study, we've just reflected a few of them here. And they break into three major categories: 100% cloud services, as shown on the left. All the way on the right, 100% in-house managed services, where organizations are really trying to incrementally develop off of infrastructure they already have and is resident on-premise. And then there are organizations in the middle that are looking to do things that we refer to as hybrid, where they're doing cloud for a lot of things, a lot of off-premise software as a service things, but they're relying on in-house managed capabilities for particular business needs that are not suitable to run in the cloud or have higher or more specialized security risks. However, they do embrace this concept of complete mediation and apply that broadly across these systems, even if they are accepted networks. We've looked a little bit at the vendor technology and building blocks that are popular out there. If you go to Google and do a search on Zero Trust product, you get a big long list of products back. And we've tried to group them into the primary aspects of our Zero Trust components that they relate to. We'll note a couple of things. The ones that have already been certified FedRAMP High or have a red box around them. We think FedRAMP High certification is important because it means that those products have gone through a fair amount of security testing. We'd hate, in the pursuit of making your cybersecurity operations better and more zero trust, for you to introduce a product that itself has a zero-day vulnerability associated with it. We wouldn't want you to introduce an Achilles heel by trying to make the system better. And FedRAMP High is one way to make sure that what you're putting on the system is a very secure product and system. We expect this market space to evolve to have more FedRAMP High certified products over time. And the other thing we'll point out is that really, while there are many tools and capabilities for building policy and orchestration, there's nothing really ready out of the box for that. That's something that organizations have to implement as they tie together these various components of the Zero Trust framework together. Just some findings from our study of these implementations and the organizations that we've talked to. We think that for organizations that are just beginning their journey towards zero trust, that they should focus on identity verification and access control first. We think that it could be quite powerful. And where possible, carefully migrate to secure cloud vendor provided services that will improve scalability and reliability. Lots of vendors offer these products, as we just talked about, but not all of them are yet FedRAMP High certified, and we think that's going to be important. Cloud services can offer scalability and robust operations, but they may not meet all mission needs, particularly for certain types of critical infrastructure and mission systems. But the idea of enabling exception networks is important for hybrid approaches. And then lastly, all of these implementations have required the organizations that have adopted them to make changes to how they think about IT management and cybersecurity operations, as well as the culture of their users, to know that in some cases they won't have unfettered access to everything on their local area network. They're going to have to do policy checks and verifications at various points in time. We wanted to take what we learned from these implementations and apply them to use cases that are relevant for the US government. And so we defined several different use cases here. A way of thinking about them is to think through not just their cybersecurity needs, but also the functional needs of those systems. And we looked at enterprise networks, critical infrastructure, one particular type of one, an air traffic control system, and then mission systems that perhaps the Department of Defense would be interested in. And we looked at some categories of those that focus on intelligence, surveillance, reconnaissance, and command and control. We came up with a way of thinking through these requirements as indicated in the table here. I will draw your attention to thinking through the security violation concerns of priority is very important. What are your most important concerns for each one of these systems will be different. In some cases, like an enterprise network, it may be confidentiality is the top concern. Critical infrastructure, particularly one related to flight safety and efficiency, like air traffic control, would be availability is very important. And still others may favor the integrity of the information on that network, like shown on the right in the mission system. So we used this approach as we went through and applied what we learned from the implementations to these various use cases. Regrettably, the details of this are a subject of another presentation. But we can draw some high-level recommendations from them. It's important to think through the zero trust requirements in a context of the system that they're going to be present in. What are the actual functional system performance requirements? Prototyping testbed activities to evaluate those zero trust capabilities are really important, especially so for critical infrastructure and mission systems. For example, we think that certain approaches to identity verification called ICAM and multi-factor authentication in certain types of environments where network connectivity is not a given all the time and can be interrupted, could be particularly challenging and needs to be worked through with some experimentation, perhaps some research and development. And then having a process for doing red teaming during exercises is really important. And these aren't just to find the oopsies that people didn't secure. This is about hardening the system to learn from it and turning that into actual effective improvements that can be rolled back into the system design and operations. And lastly, we think that a long-term research roadmap for zero trust is very important as well. And we'll summarize. So zero trust seeks to address cybersecurity risks inherent to the operation of computing systems. The risk posture and zero trust implementations will vary across different organizations. There's lots of products and processes out there, but they all require cultural and organizational change to implement successfully. We think that the government guidance should include a few canonical examples of zero trust architecture that have broad applicability to the government. And we think that an engineering team that could provide design guidance to government agencies, particularly those with small IT and cybersecurity departments, would be very beneficial. Initial efforts towards zero trust should focus on identity verification and access control. We think that's where the most bang for the buck will happen in the short term. And that as those networks evolve towards zero trust, they'll learn more about what they're doing and apply additional functionality that we talked about today. Testbeds should include challenging adversarial testing. We think that DHS's CISA organization could be a good place to retain 3 to 5 of these independent industry-based teams that might operate similarly to red teams operated by the National Security Agency. And we think that future R&D investment opportunities bound in terms of applying zero trust concepts to critical infrastructure and mission systems, as well as moving beyond zero trust into where our adversaries might be evolving. Thanks for your attention today.